Okay, so we might as well make a start. So I want to start off by acknowledging the traditional custodians of the country throughout Australia and their connections to land, sea and community. And we pay our respects to elders past, present and emerging, and extend that respect to all Aboriginal and Torres Strait Islanders peoples present at today's meeting. So my name is Francis. I'm the current president of the Canberra branch of Stats Society Australia. Thank you everyone for coming into this joint meeting between SSA Canberra and Canberra data scientists. It's also fantastic to sort of see people coming in early and having some mingling with their sort of virtual pre-drinks and nibbles. I guess in Jeff's case, real drinks, which is fantastic to see. And so before I pass it over to Yan Chang, who will say a little bit more about Canberra data scientists and as well as chair to the meeting, I just want to give a quick spiel about SSA for all those who aren't aware. The Civil Society of Australia is the national body that represents all statisticians and data scientists from sort of all aspects and all fields and disciplines. And if you want to know more about conferences, meetings, workshops, events, and all that cool stuff that are occurring both nationally as well as within your local state and or territory, please visit statsoc.org.au and you'll be able to find more information about all the events taking place, how to become a member, and how to get involved and give back to the statistics and data science community, both locally and nationally. I guess one thing I forgot to say as a bit of housekeeping is that when Marcus starts to speak, it'd be recommended if you mute your mic so that we don't have any echo and background noise. If you do wish to speak, obviously please unmute. Otherwise, yeah, please keep your mic muted. That would be much preferred. Okay, so with that, I am done and I will pass it over to Yan Chang.
Thanks, Francis. My name is Yan Chang. I'm one of the organizers of the Canberra Data Scientists Meetup. And we have around 800 members, most of them located in Canberra. As data scientists or analysts, in government agencies or with private companies. We have been co-organized joint seminars with the Statistical Society in the past 3 or 4 years. We hold a joint seminar each year, and yeah, we thank I like to thank Statistical Society for their support. Today the talk will be on missing data imputation using supervised machine learning. So the speaker is Suresh, and he is a data scientist and economist in the Analysis and Insights Division of the Department of Industry. Max has rich experience in data science and analytics, and he has also been a former visiting scientist at CSIRO Statistics 1. He specialized in applying data science techniques to structured and unstructured data to support government decision making. Max has been working with a couple of government agencies like Treasury, ATO, Department of Education. He has also been seconded to PMC before and a couple other agencies. Yeah. Today's at today's talk, Max will present his work on missing data imputation with 12 machine learning algorithms and his results on experimental evaluation and comparison of them. Okay, over to you, Max.
Great, thanks for that introduction, Yan Chang. So today I'll just like to talk through our paper, Sharpening the Blade. And then I'd like to discuss Pi-impute, which is our Python package that we created to help analysts impute missing values in their data sets. Okay, so just a little bit of information about myself. So my name is Marcus and I'm a data scientist economist at the Department of Industry. I've got my contact details here, so you can always or check out my GitHub. And yeah, as Yan Chang mentioned, I work at the Department of Industry, Science, Energy and Resources, and I was a former CSIRO data fellow. So this is the agenda that I have for today. I'll just give an introduction of our paper, discuss the data set, our methodology, go through some of the experimental results that we had and some conclusions. I'd then like to run through a demonstration of the Pi-impute package that is now publicly available in open source, and then go through a bit of a live demonstration on how you can start to apply machine learning methods to impute missing values. Okay, so we'll just start from the introduction. So first of all, what is BLADE? So BLADE, the Business Longitudinal Analysis Data Environment, is a national statistical asset, and the current BLADE asset contains data on all actively traded sectors from 2001 through to 2017. And it's sourced from ABS surveys, the Australian Tax Office, the Department of Industry, and as well as IP Australia. And at its core, BLADE is essentially a collection of ABS surveys, as well as government administration data that is joined together by an integrating spine, and that makes up the BLADE dataset. And BLADE provides researchers with an opportunity to analyse the trajectories of millions of Australian firms. So it can help us understand firm performance and dynamics, business demography, firm characteristics. It can also help us to answer some policy questions and evaluate how effective certain government programs are. Okay. So, however, like with most data sets, BLADE does suffer from some missing values. So rather than dropping missing features, what we like to do is we wanted to examine whether data imputation would be suitable using a variety of machine learning algorithms ranging from linear all the way through to more exotic methods such as neural nets. And the main motivation of this research is to assist BLADE practitioners to select and implement advanced imputation methods, equip practitioners with an understanding of the impact different methods will have on its accuracy and reliability, as well as the expected processing times from running such algorithms, and also to showcase some of the relative performances of lesser known imputation methods. Okay, so data and methodology. So a de-identified extract of BLADE was made available in the ABS Data Lab, which spans the full 15 financial years and contains 28 continuous and categorical features. And the 2015-16 data that I was using had around 8.1 million rows. And the categorical features include the indicative data items, which are things like the timestamps, the identifiers, the industrial classification, such as the ANSIC codes, and the type of organization. The continuous features were sourced from the business activity statement and the PAYG statements. And these included features such as the turnover of the firm, the exports, the capital expenditure, non-capital expenditures, salaries, wages, and full-time equivalents. Okay, so here in figure 1 is a snapshot of the entire BLADE extract for the 2015-16 data using a nullity matrix. So the nullity matrix converts tabular data matrices into Boolean masks based on whether individual entries contain data, which evaluates to true, or left blank, which then evaluates to false. And as you can see, the first 8 vectors are completely dense, which indicates that there are no missing values there. However, when you move towards the right, you can start to see that there's increase in sparsity over some of the more important features, such as those found in the BAS and the PAYG statements. And in some cases, firms may not necessarily have a value for these features for legitimate reasons. However, in other cases, it could be missing due to the matching process through when Blade was created. And since Blade is put together from a number of sources, its missingness pattern is unknown and sometimes a bit difficult to determine. So here in figure 2, we probe the underlying structure of the missingness across features illustrated by a nullity correlation heat map. So the nullity correlation heat map ranges from a value of 0 to 1. So here, for example, the blue tiles would indicate perfect correlation, meaning that if turnover is fully observed, then we would also expect to see the capital expenditure to have the same properties because its correlation is 1. And conversely, the dark red tiles indicate lower or near 0 correlation, which is closer to an assumption of missing at random. And these are features that become high value targets for imputation. So the data analysis is performed in the ABS data lab using Python. Based on suggestions by domain experts, we pre-processed the data by filtering out businesses with turnover, wages, and FTE that are not positive. This produces a dense matrix of businesses that are deemed to be actively trading. And all features are then scaled using a logarithmic transformation. So here in figure 3, I will go through the repeated k-fold cross-validation framework. So you can see that the data is then partitioned into a 90% training block, which is the dark blue block. And then the remaining 10% is then reserved for testing and validation. The data is then cut into 10 folds and shuffled prior to each repetition, resulting in a different split of the data each time. After each repetition, performance metrics are computed to assess the imputation performance from the models, from the machine learning algorithms. The entire process is then repeated a further 10 times, which then mitigates the risk of any unbalanced folds. So for example, if there's a really large firm that is found in one particular fold, the fact that it's repeated a further 10 times means that it's further randomized. And the scores from all of the repetitions are then finally averaged, yielding a robust assessment of each model's imputation performance based on the learning process. And also from the feature input from the matrix. Okay, so the data and methodology. So here we have the supervised learning algorithms that we used, so that you can see that they range from the linear regression to decision trees, and then through to the bagging regressors, such as the bagging regressor, extra trees, random forest, and then multi-layer perceptron, generalized additive models. And there are a number of performance metrics that you can use. And the ones that we use for this analysis are the mean absolute error, the symmetric mean absolute percentage error, root mean square error, mean squared error, and adjusted R squared. And the way that we set up our experiment is a 12 by 3 by 2 by 2 design. So we compare 12 algorithms against 3 different input feature matrices. And these are the three features, 7, and then we use all 14 features in the data set. Use those features to then impute the target, and we use 2 different targets, the first being the turnover and then the second being the FTE. And we also wanted to see how the results would differ using different time spans. So across 3 financial years and then across 1 financial year as well. And all of these experiments were conducted in the ABS data lab, providing a shared Intel 2.2 gigahertz CPU with 133 gigs of RAM. Now I'll just go into the results. Okay, so we first examine the turnover as the target feature for imputation, and we compare the results for all algorithms, all input features and all time spans. And in all cases, the 14 set of features performed better than the 7 and the 3. And this is because we're using all of the data available. So in table 2, we present results from the 14 features and examine the impact of the number of the input features on its performance. And using our performance metrics that we've just touched on, you can see here that the ensemble algorithms produce clearly better results than the other regressors. So the numbers here that I've highlighted, you can see that the bagging regressor, extra trees and random forests consistently producing the lowest mean absolute error and root mean square error. And the symmetric mean absolute percentage error is at its lowest. But interestingly, if you look at the amount of time taken to calculate these results, there are orders of magnitude larger. So it's there is a bit of a trade-off in terms of the processing times versus the accuracy. Okay, so the experimental results. So focusing on the top 3 algorithms and using the linear regression as the baseline. So we now compare the relative performance corresponding to the 3 different input features. So in the base condition, we use the 3 features and measure its errors, and then see how that changes when we apply 7 features and then all of the 14 features. And in figure 4, we can see that the mean absolute error decreases only slightly for the linear model, from around 5% from the 3 to 7 features, and then around 17% from 3 to 14 features. However, however, there's more of a dramatic reduction in the errors when we supply all of the features to the ensemble algorithms. And you can see that in terms of the dark blue bar there, where the errors drop substantially. And we see this across in figure 5 as well, when we measure it against the root mean square error. So based on these findings, we set out to assess the impact of the prior knowledge by considering different time spans to see how these algorithms will perform when we provided only just 1 year of data as opposed to 3 years. Okay, so in some cases, a single year of data may be available for imputation. And we wanted to know how robust these methods were with just 1 year versus 3. So here we can see that the random forest and the bagging regressor, which we highlighted, surpass the other algorithms in terms of its performance, in terms of its errors, and are very similar at 0.062 and 0.063. And coming in at 3rd place is the extra trees regressor. Not as close as the random forest at 0.062, but still relatively close. Our results show that the lack of time series data affects the algorithms to different extents. So the bagging and random forest registers a drop in performance of around 5% using 1 year of data. However, with the extra trees regressor, from 3 years of data down to 1 year of data, the errors worsened by around 12%, indicating that there is maybe a higher dependency of time series information for that particular algorithm. Okay, so moving on to the FTE feature. So as illustrated here in figure 6, the difference between the algorithms are smaller than it was for turnover. Performance still increases as more input features are used, with the best result achieved by the extra trees regressor using all 14 features, which registered a mean absolute error of 0.06, which is our lowest error score. The differences in results obtained across the targets with different distributions help us to qualify how resilient these algorithms are and hence their potential applicability to other data sets. So in essence, the best performing algorithm managed to reach similar levels of performance as more features are added, indicating that more features are indeed useful. However, in some cases, the gain is pretty minuscule, and noting that we could drop some of those features in order to gain extra time, to decrease the processing time involved. And just turning on to the processing time, because I think it is rather interesting. So here in figure 7 shows the elapsed processing times for training and imputation of the blade data, and using the three financial year data set and all 14 input features to impute the turnover target. And so we can see here that the first 5 bars, which are the linear models, they have a relatively lower processing time. In the chart here, I've presented it as in log seconds, but in terms of the actual wall time, it was ranging from between about 1 minute to 1,400 seconds. However, when we consider the ensemble algorithms, which we found to produce the more accurate imputation results, the processing times were around 55 times longer, ranging from 2,000 seconds up to about 18,000 seconds for the random forest. And the clear outlier here was the multi-layer perceptron. The neural net took over 85,000 seconds to train and to impute, and the results were not overly, was not one of the top performers. So I thought it was quite interesting to see how long it actually takes to run these algorithms on a large data set such as Blade. Okay, and just to sum up some of the key findings from our study. So we conducted a comprehensive experimental evaluation of the machine learning based imputation algorithms. And what we found was that the extra trees regressor and bagging regressor and random forest consistently maintained high imputation performance over the benchmark linear regression and across numerous performance metrics. And so we would probably recommend that using the extra trees regressor over the others because of its shorter processing time. Therefore, it's a bit more efficient, computationally efficient. And in this study, we've hoped to shed some light on some of these lesser known algorithms and how they perform in a test environment. And that brings me to the next part of the presentation, which is on the Python package Pi-impute. So,
sorry, Marcus, sorry to interrupt. Your voice fades out sometimes, and I think maybe can you check audio setting or maybe switch off your video temporarily so that we can have better audio quality.
Sure.
Okay, thanks.
Is that better?
Yes.
Thanks. So, yeah, so as I was saying, we developed a Python package called Pi-impute to help us impute missing values in data sets using a number of imputation strategies. So it's a Python 3.7 package, and its aim is to simplify the task of imputing missing values. And some disclaimers is that it's best to do your pre-processing on the data set before using the Pi-impute. What Pi-impute does is it harnesses scikit-learn in Python, which is a major supervised learning algorithm major machine learning library in Python. And Pi-impute is a bit of a wrapper over scikit-learn and allows us to perform machine learning imputation relatively quickly and with low level of coding. So essentially what it does is it gives the users what they want, which is so you ingest your data, set a target, pass in a feature matrix, and then select your chosen imputation strategy. So Pi-impute supports a number of imputation strategies, which includes univariate methods, generalized linear models, bagging and boosted tree methods, as well as a neural net. And we also have support for a number of an extensive array of performance evaluation metrics. So you can see all of them there. The main ones that we use were the mean absolute percentage errors and the mean absolute errors. But we do support a large array of these performance metrics in Pi-impute. So to start using our Python package, there's a number of ways which you can install this. You could navigate to the Python package index, pypi.org. So I provided a link there. And you can search for Pi-impute released on the 17th of March. And from there you could download and install the wheel and tarball file. Alternatively, if you prefer using pip, you can pip install Pi-impute from the command line. And an alternative way to install the package would be to go to our Cyro Data61 Bitbucket repository, and using Git, you could clone the repository onto your machine and install it there. And here's a sample of how you could install the package. Okay, and to start using Pi-impute, you need to pass through a config.json file, and I've provided a template which can be found at this link here. But essentially what it does is it looks like this here. So you tell Pi-impute where your data is, the path of the data set, and then you specify the feature list. So for example, we want to pass in the turnover, wages, and sales, for example. And the target that we want to impute is, let's say, the FTE feature. You can choose to skip some columns or restrict the number of rows that you take in, remove any duplicate rows if there are any, and then specify where you would like your imputed data set to be written to. And then along with that is an evaluation sheet, and that will produce the performance metrics for that machine learning algorithm. So I'll give you a bit of a demonstration. So we'll look at some public data here. So I looked at some of the house prices data from Kaggle, and I chose a simple one just for this example. So it was house prices in Taiwan, and you can see here that the features are the date of the sale, the age of the house, the distance from the house to the train station, the number of shops nearby, the latitude and longitude, and then the house price, which has 25% of the 25% missing. Okay, so here I have prepared my config.json file, just like I just mentioned earlier. So you can see the path where the data is sitting and the features that we want to use to impute the house price. And then I've specified where I'd like that to be written to. And then you can specify your chosen imputation strategy. So using your domain knowledge and experience, if you feel like you would like to implement a random forest based on your review of the literature and your use case, you can go to the default strategy and change that to random forest regressor. You can also specify which performance metrics you would like Pi-impute to return to you. And then you can collaborate the repeated k-fold cross-validation metrics. So you can say you want to change the number of splits from 10 to 5, or you want to increase the number of repeats from 1 to 5 or 10. So that's where you can change those parameters. And then lastly, in the command line, when you're in the directory of where you've installed the package, you would call in Python Pi-impute /imputer.py and then pass in that config.json file. And what you will see is 2 lines that'll be printed, the imputed data and where it's saved, and then the metrics and where it's saved. And then in your working directory, you will see the new data frame with the missing values appended and an accompanying Excel sheet with the evaluation metrics. So this is just an example of how the data looked before using Pi-impute. So you can see here that there is some missing values on the house prices. And then after using a bagging regressor strategy, you can see that there's now a new vector appended adjacent to where the missing values were found, with the predicted imputed value, which analysts can then choose to use for further use. They can use it in various models or to plot in graphs. And what I would like to do now is I'll just show you a live example using my Python terminal. So I'll just come out of the presentation now, and I'll just go into VS Code. And I'll bring up Anaconda. Okay, so here I'm in my Pi-impute environment that I've created. And from that environment, I open up VS Code, which is my chosen Python development environment. And you can see the 2 files here, the config file and the imputer. So here I've decided that I want to use the XGBoost regressor. I want to see how well does XGBoost go in imputing this missing value for this data set. So I've changed the default strategy to XGBoost regressor. I jump into the config file and just verify that I'm happy with everything. So I'm happy with my feature list. I'm imputing the house price, and I want those files to be written into this directory. I then jump into the terminal just down here, and I type in Python Pi-impute /imputer.py config.json, and then you press enter. And then you can see that has been written to the directory. So now if I go into my output, we can see here that at 6:38 p.m., the data set was written and it was imputed using the XGBoost algorithm. So here we can see the missing values for house prices. And then we can now see that the imputed values are appended adjacent to where those missing values occur. And so when there are no missing values, like you can see here, obviously there's no imputed value. Now, if we want to assess how well this was at imputing, we would then have a look at the accompanying sheet, which is the evaluation. And from here, we will see that it took about half a second to perform that imputation with its R-square, its mean absolute error, its percentage symmetric mate. So it's about 13.4% of error there. and you can customize this list to include your desired performance metric. Okay, so I'll just jump back into the presentation. So I'll just talk about the next steps. So Pi-impute it's a lightweight Python package at the moment. We are looking at collaborating in the open source environment and working with our maintainers to add in more features based on user input. We would like to have more imputation strategies to support as many strategies as possible. And one of the things that we would like to do is to perform hyperparameter tuning. Now, this is actually proving to be a bit challenging because if the data set is very large, the processing times can really blow out when we're trying to tune the hyperparameters across a grid search. So we have a bit of a goal to try and incorporate some GPU support if possible. And ultimately, we'd like to start to try and use Pi-impute on some of our departmental data to see whether we can at least impute some values, obviously with some disclaimers. They're obviously introducing some errors into the data set when we try to impute. It really does come down to what it's being used for. So if the imputed values are going to be used in a forecast, then perhaps that might not necessarily be the best thing to do. However, if it's being used in a chart to smooth out a chart, then the errors may be a bit more tolerable. So yeah, we'd like to start to use Pi-impute on some departmental data and to see how it performs. And on this last slide, I've just added some useful resources. So here's the link to pipy.org, where you can download Pi-impute, and our Bitbucket repositories here, a link to our paper if you would like to see all of the results and in more detail. And I've also got a link to my LinkedIn if you would like to get more updates. Okay, so that brings me to the end of the presentation. I'm happy to take any questions and or comments.
Marcus, if you don't mind, I have a question about the pre-processing step. So you said before using Pi-impute, you recommend pre-processing the data.
Yes.
Yep. So I just wanted to know, like, what is involved in pre-processing the data.
Sure. So at the moment, Pi-impute essentially does the imputation right at the end. So what I mean by that is it's not a package that can perform very bespoke pre-processing that you may need in your projects. So for example, if you're in Blade and using Blade data, it's best to get the data set in as best shape as possible. So transforming the data first, choosing the features that you want, and then passing a clean data set through to Pi-impute, so that it can just focus on taking in your processed input features. So if you would like to use, say, for example, lagged variables, then you'd want to create a data frame with all of the variables that you're happy to use for the imputation, and then simply pass those features in the config.json file so that Pi-impute can do just the raw imputation for you. So I guess what I'm trying to say here is that Pi-impute is definitely not a silver bullet. It does require statisticians to think about their domain. It does require them to bring the best processed data as possible. And then when you do need help on the final imputation, then as I've demonstrated with that test data set, you would simply pass through those those features and then impute the target.
Thanks.
Yep, thanks.
Marcus, there's a few questions in the chat that you might want to look. Thanks.
Sure, yes, I haven't looked at that. Yep, so I'm just reading through some of the questions. Won't be long.
And Max, I suggest maybe we can start from the bottom. You know, there's a question from Ray regarding whether the missing data is are they missing at random or not?
Yeah, so at the missingness at random, we don't really know some of the missingness patterns. What we do try to do is we aim to look at firms that are actively trading. So we do that by checking that their turnover and wages and is positive, which would indicate that the missing FTE value, which we are trying to impute, should actually be a positive one. So in that case, it would not be missing at random. Because we would be expecting it to have a missing, to have an actual value. And yeah, so, yeah, and in terms of the question about considering alternative imputation, what we wanted to do was a bit of an evaluation study to see how things like XGBoost, decision trees, and random forests would perform in a bit of a closed environment. There were certainly other ways of imputing FTE through more linear models, and some of our other colleagues have had a go at doing that. But what we wanted to do was we found a bit of a gap in the literature where there wasn't really a comparative study of how these new algorithms were faring at imputation. So we wanted to see how XGBoost and decision trees and random forests would perform. At the time that we performed the analysis, there was a bit of limitations in what we could do in the ABS data lab. So we didn't have all of the packages available at that time. But now that there's been more investment by the ABS in the data lab, there's certainly scope to implement XGBoost in our paper, which we didn't do at the time. And looking at the literature on other missing value imputations, we did find encouraging results on XGBoost and random forest, and that's why we decided to pursue those strategies.
Okay, thanks, Max.
Marcus,
Yes.
this is Junmei. Sorry. Hi, Marcus. This is Junmei from the ABS. So I have a question about the first part of you comparing different algorithms. You compared the algorithms on the data set with 14 variables, and you impute the FTE and the turnover using the others. And one of the algorithm actually performs better. And if we want to impute other variables, is it likely that another algorithm will perform better? And also for the second part, when you impute the house price data, is it likely that, did you compare other algorithms as well? Is it likely that another algorithm will perform better?
Thanks for the question. Yeah, so on your first question, yes, that's correct. We used all of the 13 features and imputed the turnover and then the FTE. Yeah, sorry, could I just get you to repeat the first question again? I think I might have missed it.
Yeah, my first question is, you are imputing FTE. However, if we want to impute another variable, the missing value in another variable, is it likely that another algorithm will perform better than the one, than the one that's better for the FTE?
Yeah. Yeah, so the good thing with the Pi-impute package is that you can simply switch the target to another feature. So, for example, you could use wages, you could impute wages if you needed to, if there was missingness in the wage feature, and you could use FTE as an input. It's probably better to impute the feature that has the most missingness. Because then you would need to, because you couldn't really use the feature with a lot of missingness as an input feature to another imputed value. But certainly with this Python package, it allows us to very quickly see how the algorithms would perform by just simply switching the number of features or the different set of features or a different target. I would suspect that the ensemble algorithms that we've tested quite a bit here, they consistently perform better, mostly because they tend to build a large base of weakly correlated trees, which then when added together performs very well. And that helps to address any overfitting issues. So one of the weaknesses with for example, a decision tree, is that if you set the parameters in such a way, we'll divide and conquer the data set into as many decision trees as it needs to classify or to split the data. However, with things like the random forest, XGBoost, bagging regressors, there's actually a cutoff limit to how deep the trees get, which then prevents the overfitting issue. And because you can control how deep the trees are becoming, you then develop a series of shorter trees, which then can help us address the overfitting issue. Yeah, and then onto your second question about the house price data. Yeah, we can definitely switch around the targets and the features and explore how it performs. And I think that's one of the goals of developing Pi-impute, is that we can very quickly do this through a loop, and the researcher can see how the imputation results are faring across a number of algorithms very quickly. And in terms of expanding to other learning algorithms, it's actually very simple to do. When you do download the Pi-impute package, you will see in the first part of the code where the imports are. So I import like sklearn ensemble, and you can see all of the ensemble algorithms are imported. If you don't like that and you want to import your own, I know that there are a few fancy algorithms now, like cat boost and light GBM, which are some gradient boosting methods. You can import those in Python in the import section of the code, and then as I demonstrated, where I had the default strategy, you could simply change that to your desired algorithm. So even if you have created your own algorithm, we can import that into Pi-impute and then change the default strategy to that, and then run the imputation on your bespoke algorithm.
Thanks, Max. Yeah, that sounds great.
Thank you.
Marcus, I think just to finish up, there's a few more questions in the chat. And I think if you can sort of give, I guess, some answers or some brief answers to those, that'd be much appreciated. Thanks.
Yep, sure. So I think just in response to Jintao's question, in Blade, we haven't seen any researchers that have done a comparative study on imputation performance, which was one of our motivating reasons for doing this research. We wanted to see how machine learning methods would fare in Blade. But having said that, there is quite a bit of literature around on the performance of random forests and other tree-based methods. So when we were undertaking this research, we were quite pleased to see that it was somewhat consistent with what we were finding in the literature. And in our paper, we have a literature review section, which you can see other papers that have done a bit of a summary of imputation methods. So I'm just looking at, so is Blade designed based on the concept of semi-supervised learning? Blade is more, I mean, as you would know, it's a longitudinal data set. Not sure whether it's designed for semi-supervised learning, but we wanted to see how it would go, how it would perform with some of these methods. To the best of our knowledge, linear models were used, fairly simple linear models were used to impute things like FTE over the last couple of years. So we just wanted to see how these new methods would fare and whether it would be an improvement on the current methods. Yeah, I can send the paper to your email. Just to answer, I think it's Wei's question. Yeah, in our example, yeah, I did use the XGBoost regressor for the house price data, but in our paper we didn't end up using that. It was because at that time we couldn't actually import many Python packages into the data lab due to various security reasons for installing packages. But certainly leaves the door open to do a bit of an update. Yeah, I agree that light GBM, based on the literature review, is a lot faster and potentially more accurate in some use cases. So yeah, definitely some options there to consider. Okay, I think I've answered most questions. Okay, yeah, thanks everyone for listening, and we encourage you to try out our Python package, and if you have any comments, I really want to try and expand it, so we're happy to collaborate with other experts in the field and with the ABS. It's open source now on Bitbucket, so feel free to create a branch and yeah, look forward to collaborating in the future. In terms of my GitHub link, I can send around this set of slides for everyone, and you have my GitHub details and my LinkedIn there. So looking forward to collaborating, and I'll send these slides over to Francis to distribute to everyone.
Okay, thanks, Max. Excellent talk, and also a nice demo of the Pi-impute package. And as Max said, the package itself is available on Bitbucket. You can, if you're interested, you can install it and give it a go. And so yes, thank you guys today. Is attending this seminar in the evening, and and this is the first time for me to run a webinar. I'm not sure, maybe Francis has got a few, maybe have already got experience before. And yeah, the seminar went well, although there's a little bit of feeling out voice sometime, but yeah, it went out successfully. Yeah, thank you guys for your attending. And so Francis, do you have anything to wrap up?
No, thanks, Yan Chang. Thanks, Marcus, for giving this wonderful presentation. And thank you everyone for hanging around. Have a good evening, and we'll see you all at when possible, I guess. Thank you.